Welcome to the 8th and final video in this series on rational expressions, solving equations. Before we get into the solving of equations with rational expressions, let me give you something as a resource you may want to look at before this. This video that you're going to see relies heavily on your ability to easily solve quadratic equations. In other words, you have to be good at solving quadratic equations by the factoring method before you can expect to solve equations with rational expressions. So you may want to check out that video before starting this one. If you're not sure what that is, here's a quick test of whether or not you're prepared for this video. If you were given an equation like this, by the way is not the topic that we're specifically solving today, but if you were given an equation like this, would you know to quickly set it to 0, factor, use the zero product property, and get two solutions to a quadratic equation like this? If this seems pretty rudimentary and basic algebra to you, and there's no struggling here at all, you're ready for this video. The more you're struggling with these ideas, the less prepared you are for this video, so you may want to consider going back if you've jumped ahead too far. Chances are the fact that you've opened this video means you're good at quadratic equations by factoring. Assuming that's the case, let's proceed. Here's our first equation with rational expressions. And before we start, let me point out a fundamental difference between video 8 and all the videos before it, videos 1 through 7. In videos 1 through 7, our variable x never attained a particular value. In fact, it represented virtually any possible real number, and we never really cared what x is. But this is the first time that an equal sign has showed up in the problem, and that implies that we're looking for a specific value or values of x that will make this equation true. So unlike all the other videos, the equations video, video 8 here, is showing you how to solve an equation to find out that x is a specific number or specific numbers. That's our goal. Okay, notice this equation has fractions. Equations that have fractions can be more easily solved if we can turn them into equations that don't. But that requires getting rid of our denominators. And if we want to get rid of our denominators, we need to know what the factors in them are. So the first thing that I do as my step 1 on a rational expression equation is I factor all my denominators. You'll notice in this case only one of the denominators is factorable at all, so we're good on step 1. Step 2. Let's start clearing fractions. Here's a concept. If we want to clear fractions and make this a non-fraction equation, I have to take any factor in my denominator and get rid of it. So that means I need to get rid of the x minus 2 and the x minus 4 in some mathematically legal way. Let's start with the x minus 2. In order to get rid of the x minus 2 in the denominators, I'm going to multiply every term in this equation by x minus 2. This is effectively the same as multiplying the entire equation by x minus 2. Now when I do that, let me rewrite that in a more horizontal fashion. Notice these two expressions are the same. By doing that, by choosing to multiply by x minus 2, I can simplify this equation down to this one. Let me explain. Notice in this first term, the x minus 2's effectively cancel, and you can see that by simply interchanging the order of factors and making a unit fraction. X minus 2 divided by x minus 2 has a value of 1, thus the cancellation. A similar logic shows how this reduces over here. By simply rearranging the factors, I've turned this into an expression times 1, x minus 2 over x minus 2 having a value of 1, and then reducing to the result you see at the bottom. Okay, good enough so far. Let me move some stuff around and make space. Okay, that's the same thing we had before. Now, I still haven't cleared my fractions. I still have a factor of x minus 4 as a denominator. And remember, clearing fractions is the same as clearing denominators. So, how do I get rid of that x minus 4? Only one way to do it. Multiply every term in the problem by x minus 4. I'm going to rewrite that horizontally. Take a moment to notice that those two are the same. And the nice thing about choosing to do that is that it simplifies to this. Let me point out the one change here. Again, by simply rearranging the factors, I'm able to see the cancellation of the x minus 4s. Okay, let me make some more space so we can proceed. All right, nothing has changed. I've moved some things around. Now here we've come to a pivotal moment in this problem. Notice on the screen, from top to bottom, I have turned a fraction equation into a non-fraction equation. I have completed step 2, the clearing of fractions, and that step is the real challenge in these problems. Now the other challenge in these problems is once you've cleared fractions, we go on to step 3, where we're going to use our linear and quadratic equation solving techniques to solve our non-fraction equation. Now, this video assumes that you have some command over that skill. And if you've gone this far in the video, you probably do. So grab yourself some scratch paper, get ready to hit pause. In a minute when you hit pause, expect to take anywhere from 3 to 5 minutes, if you're the typical student, to solve this equation. I'll see you in 3 to 5. Hit pause. Okay. Compare your work to mine. You may not have done it exactly the same way, but you should have arrived at 2 solutions, x equals 5 and x equals 1. If you didn't, hit pause again and take some time to figure out where you went wrong. And assuming you've done that, let me make some space and we'll proceed further. Now, it appears as though we've solved this equation. Here's an equation, we did some algebra, we got x equals 5 and x equals 1. And yes, we have solved it. But it turns out there's a 4th step called checking for extraneous solutions. Now we'll talk a little bit in more detail later in this video about what extraneous solutions are, but for now let me just say that they're essentially wrong answers. So we're going to check for wrong answers. In other words, we've gotten 5 and 1 as our answers. Let's confirm that those in fact are. Step 4 is essentially a confirmation step. So here's what I'm going to do. I'm going to take my original problem and I'm going to replace all the x's with 5. Let's check x equals 5 first. Notice I've replaced all my x's with 5, and now I need to confirm if 5 actually is a solution. Well, here's what I did, and I did it on scratch paper to save you from having to see it all, but I worked this entire thing out on scratch paper. I got 14/3, and so would you if you paused and did it yourself. Then I worked this thing out on scratch paper, and I got 14/3, and so would you if you did it yourself. Now, that does not mean that the answer to this problem is 14/3, but it does tell me that both sides of the equation are equal to each other, and that's exactly what I was looking for in a solution to an equation. In other words, when x is 5, both sides are equal to each other. That confirms 5 is in fact a solution. Now let's check if x equals 1 is also a solution. Taking my original equation, plugging in 1 for every x, here's what I did. On scratch paper, I worked this out, and I got 2. Actually, I worked that out in my head, and you probably could too. This one I needed scratch paper for. I worked it out. Now the details aren't shown in this video, but if you pause and work it out, you'll notice you also get 2. What does that mean? Well, it means both sides of the equation work out to the same number. Therefore, x equals 1 is also a solution to this problem. All right, I'm going to put my equation back just so you can see the problem in its sequential form. I've now checked my answers. 5 and 1 turned out to work. Therefore, there are 2 solutions to this equation, x equals 5 or x equals 1. Let's look at a second problem. Let's go through these same steps again. First, I'd like to factor my denominators. I had 2 factorable denominators in this case, you'll notice. Next, I start the tough, lengthy step of clearing fractions. I want to turn this into a non-fraction equation. So, I have to pick a factor to get rid of. For no particular reason, I'm going to start with x minus 3, that's in one of my denominators, and I'd like to get rid of my x minus 3's. To clear out the x minus 3's, I have to multiply every term in this equation by x minus 3. Notice that leads me to this. I'll pause while you see what just happened. And now I can reduce. Well, it turns out the terms in this equation reduce to these terms. Let me remind you how this works. By simply rearranging the factors, interchanging them, I was able to get 1 over x plus 2 times what is effectively 1, x minus 3 over x minus 3 being a version of 1, and thereby reducing this term here. You'll notice the reduction here by the same logic. So now let me move some stuff around, make some space. And we're ready to proceed. Notice I'm still on step 2. I've not cleared all my fractions yet. So long as I have a denominator, I have fractions. Well, I've got to get rid of the x plus 2 and I've got to get rid of the 5. It doesn't matter which first, so I'm going to get rid of the 5 by multiplying every term in this problem by 5. I'll pause a moment while you confirm that that's the same. Simple enough. But now some reducing happens. To explain this reduction, notice here I simply interchange my factors, pulling the 2 5's out and canceling them, 5 divided by 5 being 1, of course. And of course, on the right side of the equation, 5 divided by 5 is 1 also. Well, okay, let me move some stuff around and we'll continue. Nothing's changed. I've just moved some things to make space. Now, I still have a denominator. Therefore, I'm still on step 2. The only way to clear fractions is to multiply every term in the problem by x plus 2. Now, if it looks like there's an extra x plus 2 in the middle there, if you want to consider x minus 3 a single term and multiply it by x plus 2, that would work out exactly the same. It would be FOIL, and nothing would change from the result I'm going to get. But I've considered the x and the minus 3 as separate terms. Either way is fine. This turns into this. I'll pause while you look at that. And in the first term on the far left, the x plus 2's effectively cancel, becoming just 5. Here's the logic that allows me to do that. And now I'm going to make some more space. Nothing has changed, things have moved, but now I've reached an amazing moment in this problem. Notice from top to bottom, I have gone from having fractions to having less fractions to having no fractions. I have now cleared my fractions, and I'm ready to move on to step 3, using my linear or quadratic techniques. In this case, quadratic equation techniques are going to be necessary again, just like they were in the last problem. So it's time to get that scratch paper. When you're ready, you're going to pause, work this out. Expect it will take 3 to 5 minutes. I'll see you in 3 to 5. Go ahead and hit pause. Okay, now that you're back, compare your work to mine. It doesn't have to look the same, but one way or the other, you should have gotten 2 solutions, x equals 3 and x equals -1. If you didn't get those, hit pause and examine my work and yours and see what happened. Assuming you did get those 2 values, or you've now checked them, let me make some more space. Okay, now it appears as though I'm done because I've gotten down to where it says x equals these numbers. And in certain problem types, not this video, but in certain equation solving, that's it. You find out what x is and it's over. But in rational expression problems, you have to go on to a 4th step of checking for extraneous solutions, which again I'll say more about in a few minutes, but they're essentially wrong or fake answers to the problem. In other words, we've gotten to the point where it says x equals 3 and x equals -1, but we need to confirm that those are in fact actually answers to the original problem. So I'm going to take my original problem and I'm going to start by checking 3. I'm going to plug 3 into every x and I'm going to work this out. Something strange happens here. It turns out this works out to 0. And this also works out to 0. Now what does that mean? Well, you'll recall that division by 0 doesn't exist. It's undefined. And so 1 divided by 0 doesn't exist. There's no mathematical answer to 1 divided by 0. And if something doesn't exist and I'm adding 1/5 to that, I think it's fair to say the whole thing doesn't exist. So neither the left side nor the right side of this equation exist. So here's a thought that mathematicians had to make a decision on centuries ago. If there's a number like 3 in this case, and we plug it into both sides of an equation, and both of them don't exist, are the 2 sides equal? If 2 things don't exist, are they the same thing? Well, they could have chosen yes, but mathematicians have chosen, just by some sense of fairness, that if a number, such as x equals 3, is plugged into an equation and the equation isn't even calculable, then we shouldn't consider 3 a solution. So we're going to cross out 3 and call it a non-solution. It's actually called an extraneous solution. It basically means it's a wrong answer. Now let's take our original equation and now let's check if x equals -1 is a solution. Here I've plugged in -1 for every x. Now I didn't want to clutter the screen with details, but I worked out all this mess on scratch paper and I got -1/20. Then I worked out this, in my head actually, and got -1/20. Now of course that doesn't mean -1/20 is the answer to this problem, but the fact that the left and right sides work out to the same number when x is -1, that tells me that -1 is in fact a solution to this equation, and therefore I'm going to accept -1 as an answer, unlike what I did when x was 3, which was rejected. Let me put my original equation back, just so you can see the sequencing here. Now, let me clear up a couple of misconceptions about extraneous solutions, which in this case x equals 3 is such an item. It's a misconception, and I've had many students tell me, Professor Racedlo, I got the answer to this problem. X equals 3 is an extraneous solution, and x equals -1 is in fact a solution. And while you wouldn't be wrong to say that, there's sort of a tradition in equation solving that we don't mention things that aren't solutions. And if 3 isn't a solution, there's no reason to mention it. Let's think of it another way. 99, random number I just picked, 99 is not a solution to this problem. -12 is not a solution to this problem. 351 is not a solution to this problem. There's infinitely many things that are not solutions to this equation. 3 is just one of those things. We have a tradition not to mention things that aren't solutions. So never write x equals 3 with a red X by it, as I've done here. Simply don't mention it at all, and just say the answer, the single and only answer to this problem, is -1. Now that completes this problem, but in the remaining time in this video, I want to spend a couple of minutes telling you what causes extraneous solutions in the first place. Because if you're anything like me, you've gotten wrong answers to equations in your life many times. But wrong answers usually indicate that we made a mistake. But we didn't really make an algebra mistake here when we arrived at x equals 3. It wasn't a mathematical error. I mean, not in the traditional sense anyways. So I want to spend a few minutes telling you what causes extraneous solutions. By the way, if you're the kind of student who doesn't want to hear some pretty advanced mathematics right now, and you're happy just saying, you know what, I don't need to know what causes them. I just need to know to check for them and to delete them when they show up, then you're going to want to fast forward the rest of this video. In other words, bow out. But if you want to hear why they arise in the first place, let's take a couple minutes on what causes them. So what causes extraneous solutions? Well, you may recall several minutes ago in this problem, we had this, and we decided to get rid of the x minus 3's by multiplying each term by x minus 3. And I'm just reviewing what we did in this problem. And then a few steps later, we had reduced to this. Now, it turns out x equals 3 is in fact a solution to this equation. And if you want to pause here and plug in x equals 3 to that equation, you'll convince yourself, yes, it in fact is a solution. However, x equals 3 is not a solution to this equation, nor the original equation. So what's happened in this problem is that we've taken an equation where x equals 3 wasn't a solution and turned it into an equation where x equals 3 was a solution. Well, how is that possible? Well, it all comes down to us multiplying by an expression with variables. It turns out whenever you multiply an entire equation by any expression with variables, or divide for that matter, you run the risk of creating answers that aren't answers to the original problem. And to say a little bit more about that, remember our logic on how the x minus 3's canceled here? We asserted that x minus 3 divided by x minus 3 is 1. Is that true for all x's? Yes, except when x is 3 itself. So we made an assumption, and we didn't mention it at the time, but when we were going through the solving process here, and when we canceled those x minus 3's, we were implicitly assuming that x wasn't positive 3. And therefore, the conclusion at the end where we thought x might be 3 was a contradiction to that assumption. This is very advanced math. If you got lost in the reasoning as to why, the basic fact you need to know is that if you ever multiply by a variable or divide by a variable, the equation that you create might have a solution that isn't a solution to the original problem. And that completes this 8th video and this series on rational expressions.